Good, everyone. It's been a while since I posted a video. Well, I make sure that I won't miss. So, in this presentation, we are going to talk about functions. Now, I know my voice is a bit low. It's because I'm tired and I'm just trying to get this out. So, I don't have to spend too much time doing it. All right. So look, instead of me telling you about the announcements, telling you what needs to be done throughout the week, I'm just going to dive into the lesson because I feel like whatever announcements I have to tell you is automatically in the classroom. In addition to, almost all of you have a calendar of important events that you know what's going on. And not only just that, I'm always going to post it out to you in Google Classroom. So I will send you a message telling you what's going to happen throughout the week. All right, first and foremost, let's dive in. The precise definition of mathematics. This is important. We talked about it since you first met me. The precise definition of mathematics is the technique to explain, understand, and manage reality by ciphering, counting, measuring, classifying, ordering, inferring, and modeling patterns arising in the environment. This is a this is life right here. It's very important because this is what we do in everyday life. You know, you may not satisfy every part of the definition, but you you going to satisfy a part of it. You may not do all of it, but at least a part of it. So let me make sure I say that clear. All right, let's get forward and let's move onwards. Just remember, math always have two parts. Applied, real life situation, and abstract. That's the characteristics. That's the thinking part. So with abstract, we do a lot of thinking. It's something that you don't see, you don't touch. Apply is stuff that you do see and touch. So again, apply is something you can see, touch, do. Abstract is something you can't really touch or see. Well, you can see, but you won't be able to really do anything about it. All right, let me move forward. So functions. So in today's lesson, I'm going to go to an abstract and apply because I do want you to get a better understanding of applied and abstract. All right. First and foremost, we have to talk about relation. Just like in life, math is a relationship. We deal with relationships in everything we do. So, in a mathematical sense, a relation is a rule that takes input values and assign them to an output value. As you can see, you see coordinate pairs, but in math, we, we represent this in three ways. We represent this in mapping, tables, and graphs. Mapping, tables, and graphs, they're all the same exact thing. They're just different representations of those, okay? All the same things, but just different representations, but exactly meaning the same. So mapping is very abstract and you're going to see it. All right. A function is a expression, rule, or law that defines a relationship between one variable known as the independent variable and another as the dependent variable. And we're going to give you an example of it. So, when you think of a function, think of it as a machine. You put something in it, which is your independent variable. The function is the relationship piece because it does something to that x value. And then when you spit out, it becomes your y value, and that's your output or your outcome. Now, pay close attention. Y is your output, but y also have a different notation. We're dealing with functions. It's going to become f of x. So f of x is the same thing as y. So x is not the same as f of x. They're not equal to each other. So be very cautious, be very careful of that. All right. So this is the well, how you write your functions y equals x. And this is a quadratic equation we're dealing with. So the input is 0, 1, 2, 3. The relationship is what I'm doing with that 0, which I'm squaring it because 0 times 0 becomes my output, which is 0. 1 times 1 is 1. 2 times 2 is 4. And of course, 3 times 3 is 9. Again, the relationship is the operations that I do. Again, relationship is the operation of what I'm doing to that input to produce my output, which is my final answer. All right. So now let's do an example. You have an equation y equals f of x, or a function, because there is a function. What we're trying to do is identify input, our relationship, and our output. So the x is my input, so I'm going to start with 0. My relationship is the operation I'm doing, which is 4 times 0, which gives me 0, which is my output. All right, let me do 1. 1 is my input. The relationship is what I'm doing to that input, which is multiplying 4 times 1. And I do that, I get 4. Now I want you to pause the video and go through 2, exactly as I did 0 and 1. Pause the video and come back to me. Welcome back. Let's do it. So you got 2, correct? 2 is my input. The relationship is me multiplying that 2 with the 4. Then my output is the 8. Good job if you got that right. You have to be able to identify all parts of that function. Now, here's an example. Again, this is me bringing it to the applied. We haven't gotten into the abstract yet, but we will. So, working at CVS for $16 an hour, the independent variable or X is the hours I work, which is the input. The relationship is the operation of multiplying because I'm multiplying X times the 16. The X represent my hours, of course. My dependent is my output. It's the money that I made. Well, 16 times how many hours I work. So if I work 10, 16 times 10 is $160 that I would make. And that is how you do that. So now you got a applied example. Now, this is me telling you function notation. Y is replaced with f of x. Y is replaced with f of x. I do apologize that my audio is low, but I need for you to put me up on blast so you can hear me. So this is an example, and you notice that I don't have y, I have f of x. All right. So I have x squared. The input are my values. The relationship is me squaring, and the output is my outcome. And I know we did this example, but this is just me give you further details about f of x. Right? I want you to pause the video. I want you to identify the input, the relationship, and the output of this function. In fact, I want you to try this by yourself and figure this out on your own and just go back to previous examples to identify to check your work. So I'm not going to do this with you. I want you to try this one on your own. All right. I'm still dealing with the applied functions, parts, and rules. The function against the chosen value. The relationship is the operation you use. The output is your answer. Remember, it must work for every possible input value, input being your x value. And remember, it only has one relationship for each x value or input. This is going to be a point for you to have a better chance of understanding the abstract stuff. But that's where it's going to be even more difficult. All right. So now we're going to the abstract definition of a function. So we went to apply. Now we're going to the abstract. Now I want you to read this and compare the definitions and look at them sideways. All right. So a precise definition of a function is a function f is a rule that assigns every element in some set A to a corresponding element in some set B. Set A is known as the domain, and B is the and B and set B is known as the codomain. Weird, isn't it? So let's look through this and pick this apart. So your set A, when they call it the domain, they essentially saying X value. When they say B or your codomain, well, codomain is known as your Y value, which is your output. And what it's telling you that every element in set A, every element in set A has a corresponding element to B. So if you compare the definitions side by side, you could get the connection from there, which is basically saying your input and your output. So that means every X has to be used to get an output of Y. Now, I'm going to show you some mappings. Mappings, again, are equivalent to tables and graphs. There's just another form of a function. So you have three types of functions: injective, and surjective, and bijective. So bijective, we're not going to worry about this at the moment. I don't want you to worry about bijective functions yet. You're going to be dealing with that soon, but just not now. So injective functions means that every element, all the elements, go to one element in B. So one element of A goes to element of B. And when it's adjective, we call that a one-to-one function. Now let's look at surjective. Surjective is when you have elements of A, when you have two different elements of A going to the same element of B. And when it's surjective, we call it on to. Think of it as more of as a fight, meaning that when you jump on somebody, you are on to somebody, right? When it's two of you guys right here jumping on this one guy, you are on to that one guy. So that's how you think of surjective. Again, these are elements of set A going to elements of B, which two different elements of A can go to a singular element of B. And we go back to injective, we have one. You have every element of A going to every element of B just once. So there's no two elements of A going to a singular B. They are going to one. All right. So pause the video and determine is this surjective or injective. All right, welcome back. If you say that this function is surjective, you got this correct. It is surjective because you have two elements, two distinct elements in X going to a single element of Y. That's possible. You are allowed to do that. All right. This is also surjective because you have you have two distinct elements in your left going to a single element to your right. So that's also surjective. Now, this is injective because every element in red goes to exactly one element in blue. Every element in red goes to a singular element in blue. This is subjective again. Now, we've taken an abstract concept and now we're bringing it back to the applied sense because now you're dealing with numbers. So let me ask you this question. It is injective or surjective? Pause the video and see what you could do. All right, welcome back. This mapping is neither injective or surjective. It is because you have elements of x not going anywhere to the element of y. And not only just that, you have a singular element of x going into distinct elements of y, which is not allowed to happen. All right? Again, you are not allowed to have a singular x value or element going to distinct elements of the set y. Pause video and determine is it injective, surjective, or neither. This is injective. It is injective because every element in X go to exactly an element of Y. Again, every element of X goes into a singular element of Y. So this is 1 to 1. 1x, 1y. 4 goes to 16. Negative 4 goes to 16. Those are different x's. Those again are different x's. Those are not the same elements of x. Those are distinct elements of x going to y. All right, so we did that. Now let's bring it a little bit further. So in class, I'm going to give you a situation, and you're going to have to be able to bring the example or situation I give you, and you're going to have to use the abstract and apply to the situation. It could be anything I ask you or anything. You just have to be in class to know it. So we describe functions inwards and outwards applied to abstract. A big thing to remember, abstract and applied is all connects. And not only just that, when your inputs does not map to no more than one output, then your map is a function. So what I did here in that statement, I combined the the applied definition and the abstract definition. I just pretty much combine because they are all exactly the same. Now, I have a challenge for you, and this is something that you're going to have to prove. I'm not helping you on this. This is more you taking what I have taught you and taking it a step further. And yes, this is something that I will test you on. So you have to prove that all functions are relations, but not all relations are functions. Now, this is what I want you guys to pay attention to. Inverse functions. So inverse for functions, and we just going to touch on it very little here in this lesson, is when you have ordinate pair 1, comma 2, and when you flip them, or when you can flip them to 2 to 1, when you do that, that is a inverse. If it's negative 3, comma 7, you're going to flip it to 7, comma negative 3. All right? That's all they saying. That's all this is. 1, 2, and then you go to 2, 1, 3, 7, 7, 3, 4, 9, 9, 4. All right. Now, we're going to further details about each characteristic of functions because you're going to be dealing with a lot of functions. All right. So, two basic characteristics are dealing with domain and range. Your domain is all your x values from start to finish, and your range is all your y values from start to finish. Symmetry. So when you have a function that is symmetric around the y-axis, and when you see f of x is your y. So when that happens, and when it's symmetric around your y-axis, it is even. And we're going to go further into this because this means that this that I'm highlighting means that if you was to put in a negative number, it's going to be positive. Like for example, if I was to say f of x equals x squared, and if I was to substitute a negative 1 there, that means that negative 1 squared is going to be positive. So guess what? They haven't changed. The x squared is still positive. A further detailed way of looking at it is this. If negative 1 confuses you because you see x's and stuff like that, why don't you do this? F negative x. And we know that two negative signs are going to make a positive because two negative signs make a positive. You're going to have positive x squared still, so therefore it's even. Now, when it's odd is symmetric around the origin. Symmetric around the origin. So that means that if I was to plug in a negative sign or a negative 1 into my function, it's going to change it. Like for example, if I have an equation of positive x, y equals x, if I was to plug in negative 1, That means that this graph that was originally positive is going to become negative. All right. And yes, we know why I changed y, because y was easy to write. So remember, y is f of x. I just chose to go back and use y because it's just easy to write by hand. All right. So even that our functions is not based on the symmetry, it's based on the end behaviors. So remember, you look at the ends. So let's look at here. So for it to be even, that means from the left, the graph decreases, and then from the right, it increases. It goes opposite directions, so therefore it is even. Now when it's odd, looking at your end behaviors, you notice that the end behavior of the graph increases from left, and then from the right, it also increases. So therefore, it is odd because it's going one direction when you looking at the end behavior. Asymptote. An asymptote is when the graph get closer, and it get closer, it approaches something, but does not actually touch it, or it takes forever to touch. You're going to have a horizontal and you're going to have a vertical. That means that I have a graph and the curve get closer to, but it doesn't touch or it takes forever to really touch. You have that here and you have this here. Horizontal and vertical asymptote. Intercepts is when that crosses the x or y axis. Slope, that's dealing with linear functions. Change in y, change in x. To be truthful, every function has a slope. It's not just linear. Vertex is pretty much your maximum, and it's only for quadratics. Period and amplitude, we have done this with trig functions. All right. Now, let's go to the final detail of this and we will be finished. And we're going to go through all the parent functions that we're going to be covering this semester. Some of these functions we have talked about already. So a constant, you're dealing with like 5, 6, and we remember that all these real numbers are polynomials. And they are polynomials because by law of exponent, well, they could be rewritten with a variable and the exponent of 0. And by the law of exponent, anything to the power of 0 is going to be 1. So 7 times 1 is just 7. Now let's look through all the characteristics of a constant. So a constant going to have a domain of negative infinity and positive infinity. That means that it doesn't stop from left to right. It's going to keep going. So it has a domain and range. An inverse. It doesn't really have an inverse. Is even. Well, it's not really even. Let's correct that. It's not really even because it's going to, from here, it's going, yeah, it's not even. Because remember, even is going opposite directions when you look at the end behavior. I will explain that a little bit further if you need for me to do so. Now, linear functions, the domain is negative infinity to positive infinity. The range is the same thing. Its inverse function is still a linear function. The word about restrictions, I'm going to talk to you about restrictions later on. It is a odd function because if you look at the end behavior, it increases from the left, it continues to increase from the right. It's going one direction. And the unique characteristics of a linear function is slope. All right. The next function you deal with is the quadratic. So the quadratic has a domain of negative infinity, positive infinity, but it has a range starting from 0 for the y to positive infinity. The inverse, I told you guys this before, that squares and square roots undo each other. Back when we were solving polynomial equations by the square root method. Now, it is even because from the left the graph falls and from the right the graph increases, so that's why it's even. And the unique characteristic of a quadratic function is called your vertex, or your maximum or minimum, in this case minimum. Alright, so the next function is the square root. The domain of a square root starts at 0 and keep going to infinity. And the same thing as the range. Your inverse is the quadratic. Don't worry about restrictions at the moment. I'm going to talk to you a little bit more about that. It's neither even nor odd. It's neither even nor odd function. And you have to know why that's the case. Alright, now we're dealing with cube and cube root. They are inverses of each other, just like squares and square roots. So the domain, negative infinity, positive infinity, just like the range. The inverse function of this is cube root. It is an odd function because you keep increasing from the left, and from the right you keep increasing. And cube root is the same thing. And the inverse is vice versa, which is cube. All right. The rational function or the reciprocal. Now this is going to be hard to write. Now this has a unique characteristic of a asymptote. And this is not a polynomial function. This is an asymptote. So your domain is going to be written different. It's not going to be negative infinity to positive infinity. It's going to be negative infinity, and then your asymptote, it approaches, get close to, but don't touch, which is 0 for your domain. And then it picks up again. This U shape means it picks up because you have a gap. And you keep going from 0 to infinity. And the range is the same thing. The inverses doesn't have an inverse, it's still the same. The inverse of a rational function is a rational function. Now the restriction is you cannot have anything in the denominator, because just like a rational number, if you put anything in the denominator, you're going to have it to be undefined, and it's going to look like something like this. So when you see a graph with a gap like this, that means that it's undefined because of the gap in the graph. Now, both exponential and logarithmic have alternative forms and they are inverses of each other. And then they have the unique characteristic of an asymptote. Exponential functions have horizontal asymptotes only. Logarithmic has vertical asymptotes only. Alright? So, domain is all real numbers, negative infinity, positive infinity, and you know this because the exponential function has a asymptote, horizontal asymptote. Because of that, your domain is going to be all real numbers. But you have a range. A range, because you have a horizontal asymptote, is going to go from 0 to infinity. And it does not have a symmetry, but its inverse is the logarithmic functions. We'll explain to you each of the alternative forms of the exponential and logarithmic. Now, the logarithmic has a vertical asymptote. Because it has a vertical asymptote, that means that your range is going to be all real numbers and your domain is always going to be 0 to infinity. Alright? Last of this is dealing with sine and cosine. Now, sine is an odd function, and we both know that both these have the unique characteristic of a amplitude and period. That's what we know. The domain range is the same. The only difference is if its sine is odd, cosine is even. And that's pretty much just it for today's lesson, y'all. It's just that.